The theory of relativity proposed by Albert Einstein in the early 20th century fundamentally revolutionized our understanding of space, time, and gravity. It consists of two main pillars, special relativity and general relativity. Special relativity. This theory, formulated in 1905, addresses the behavior of objects moving at constant speeds relative to each other, particularly when those speeds are significant fractions of the speed of light. Here are its key principles. Principle of relativity. The laws of physics are the same for all observers in uniform motion relative to each other. There is no absolute reference frame. Constancy of the speed of light. The speed of light in a vacuum denoted by c is the same for all observers, regardless of their relative motion. This principle contradicted classical physics, which believed that the speed of light would change based on the motion of the observer. Time dilation. Moving clocks appear to run slower when observed by a stationary observer. This phenomenon arises due to the dilation of time intervals at high speeds. The faster an object moves relative to an observer, the slower time appears to pass for that object. Length contraction. Objects in motion appear shorter along the direction of their motion when observed by a stationary observer. This is also a consequence of the Lorentz transformations, which describe how space and time coordinates change under relativistic motion. General relativity, developed by Einstein between 1907 and 1915, general relativity extends the principles of special relativity to include gravity and acceleration. Its core principles are equivalence principle. Acceleration due to gravity is equivalent to acceleration due to any other force. This principle led Einstein to conclude that gravitational mass and inertial mass are equivalent, meaning that gravity affects all objects in the same way, regardless of their mass or composition. Curvature of spacetime. Mass and energy cause spacetime to curve, and objects move along the straightest possible paths, geodesics, within this curved spacetime. Massive objects like stars and planets cause significant curvature, which we perceive as gravity. Gravitational time dilation. Clocks in stronger gravitational fields run slower than clocks in weaker fields. This effect is observed, for example, with clocks on the Earth's surface compared to those in orbit. Gravitational redshift. Light traveling out of a gravitational field is redshifted. Its wavelength increases, indicating a loss of energy. Conversely, light traveling into a gravitational field is blueshifted. These principles provide a comprehensive framework for understanding gravity as the curvature of spacetime and have been confirmed through numerous experimental tests and observations. General relativity has profound implications for cosmology, explaining phenomena such as the bending of starlight by gravity, gravitational lensing, the expansion of the universe, and the existence of black holes.